Today we're going to take a look at the addition and subtraction of rational numbers. We're going to start with just addition definitions. So we have two different options when we're adding fractions together. They might have denominators that are the same or like denominators, or they might have denominators that are different. If the denominators are the same, that's the first definition, then we simply add across the top. So a over b plus c over d is a plus c over b. Okay? And it's tempting sometimes to add across the top and add across the bottom. So let me just show you a real quick picture of why that actually doesn't make any sense. And we'll just do one where the numbers are 1/3. And I'm going to do it with a circle form. So we're going to split this into 1/3, roughly speaking. It's not perfect. That's a little bit better. So if I ate 1/3 of a pizza, and then you ate 1/3 of a pizza, the total pizza that we ate was 2/3, not 2/6, right? So the denominator stays the same because the denominator is indicating the size of the shape, not how many shapes. Now, if the denominators are not the same, then it gets a little bit more difficult. So in the last section, we worked with breaking down denominators so that we could find a way to compare them for the most part. We did comparisons of numbers. Here we're going to break apart denominators to get like denominators to add them together. This is not the only way to do this, but it is a very nice way to do it because it has a structure that doesn't make me do a whole lot of factoring. So if you take a look at the visual for this, it's lovely. You actually multiply the diagonals and you multiply the bottom and you get a smiley face, kind of. Okay, so along the top to bottom diagonal, that's a times d, plus the other diagonal is b times c, and it's divided by the fractions denominator, which is the multiplication of the two, bd. Okay, do I care if you use that instead of finding the denominators a different way? It doesn't matter to me in the slightest, but it is a nice thing to be aware of as an option. And I'll use it a couple times just to make sure you're comfortable with it. So on the first example, we have 1/3 plus 5/3. And clearly on this one, we do in fact have the same denominator. So we will add across the top 1 plus 5. And 1 plus 5 is 6. Anytime we have the ability to do so, we always will reduce. So 6/3 or 6 divided by 3 is 2. So sometimes when we're working with fractions and we're adding them, we end up with whole numbers when we're done. My next example does not have common denominators. So just for an opportunity to remind you or to show you how this picture worked that I did before, we multiply along the top to bottom diagonal, so it's 1 times 3. We add it to the other diagonal, which is 4 times 5, and divide it by the two denominators multiplied together. So that's what that definition said. 1 times 3, of course, is 3. 4 times 5 is 20. And 4 times 3 is 12. So I end up with 23 over 12. Unless you're told to change something into a different form, you can leave it in what it has as long as it's simplified. So by simplified, I mean that it doesn't have anything that's divisible on the top and the bottom by the same value. Okay, so mixed numbers that are not preferable in any way, shape, or form to improper fractions. There are good and there are bad about both, but we don't want to do more work than we have to. All right, so we're okay to leave it this way because 23 is prime. It won't divide by anything that's in the number 12. So let's talk a little bit about mixed numbers then. One of the benefits of mixed numbers is that, hang on. I thought it was on my screen first, but it's a flying bug. Okay. One of the benefits of mixed numbers is they have the great connotations to real life, right? Like we think about things in mixed numbers more readily than we think about things in improper fractions. I would never tell you that there's 1/23 of a pizza left, right? That's crazy. We don't talk like that. So mixed numbers represent are more common to life, everyday life. They represent an integer combined with a proper fraction. So, as we're taking a look at an example, let me do that 23 over 12 just because we just had it. 23 twelfths of a pizza. No, We don't say that. But the corresponding mixed number for this would actually be 1 and 11/12. I'm going to show you that, remind you how to do that in a second. But it's 1 and 11/12 of a pizza. In other words, it's telling you there's a whole pizza and then there's almost another whole one, right? 11 out of 12. There's 11 slices of a 12-slice pizza. Okay, so we look at that and we have an immediate reference point of visual that makes sense to us, whereas 23/12 doesn't have that for us. So let's take a look at a couple of examples of changing both in and out of mixed numbers. So here's 14/3. So if we're taking our improper fraction and we're turning it into a mixed number, it's still advisable to go ahead and reduce it if it can be reduced first, right? 14 and 3 don't have anything in common. If it said 14 and 6, I'd divide them both by 2 before I do anything else. Okay, work with smaller numbers when you can. This one's as small as it can be in terms of those values. So when I have 14/3, it means 14 divided by 3. And you're really going to show me the division. You're going to draw it out, okay? Just like you would expect your students to if you were teaching this particular concept to them. So 3 goes into 14 how many times? 4 times. 4 times 3 is 12, and we subtract. 14 minus 12 is 2. So when we write our answer, the number that divided out completely is first. That's my integer. The remainder is my new numerator, and the denominator is the same denominator I started with, which is the number I'm dividing by on the outside. So this is 4 2/3 as a mixed number. Now, if you're going from improper fractions, or from mixed numbers back into improper fractions, first of all, if there's a negative, you just know the answer is going to be negative. I don't have to work with the negative along the way. So we're going to focus our attention on the fact that it's 3 5/8. So I'd like to show you the shortcut that you probably remember, but I'd also like to show you where it comes from because it's not super hard to see, but you might never have thought about it before. So the shortcut that we usually think about is that we take 8 times 3, which would be 24, and we add it to the 5. 24 plus 5 is 29 out of 8. And because the original value is negative, ours is as well. So it's negative 29/8. So let me actually talk about where that came from because it's pretty simple. 3 5/8 is 3, as in 3 out of 1, and 5 out of 8. That's what it is. So I can actually use that same algorithm I showed you before, where I multiply across and multiply the bottom. I get 3 times 8, just like I had 3 times 8 before, plus 1 times 5, just like the 5 I had before, and I divide by 8, and I'm still going to get the same 29 out of 8. So really it's just the addition of 2 separate numbers. But we have this nice little shortcut imagery that we can use instead. Any questions about converting mixed numbers to improper fractions or vice versa? Okay. Some properties of addition. One of the properties of addition that comes about with integers is the inverse property. So this is the additive inverse property specifically of rational numbers. So for any rational number a over b, there exists a unique rational number negative a over b, such that when you take a over b plus negative a over b, you get back 0. So every number has an inverse, an additive inverse. Even 0. What number do you have to add to 0 to get back to 0? 0. It's not exciting, but it still has one, okay? So there's always a number to add to the value we're working with to get back to 0. The additive property of equality talks about what happens when we have 2 fractions that are equal. So if we have the fraction a over b that is equal to the fraction c over d, it is perfectly acceptable to add e over f to both fractions and they will still be equal because we added the same value to each of them. So we see this used, both of these actually used a lot when it comes to solving equations. this idea of additive inverses and additive identities. These properties of equality being used. All right, so let's take a look at an example, and I'm going to do the example two different ways because there are two different approaches to what's going on. But I'd like for us to sort of recognize that we're using these properties as we do it, though we're not going to like write down property of equality. We're just going to say, hey, look, I did this. That's why I can do it. So taking a look at this one, I have x minus 2.5 equals 3.5. So if I want to get x alone, I do in fact need to add the 2.5 to the other side. Why 2.5? Well, because it's the additive inverse of negative 2.5. That's why. Why am I allowed to add it to both sides? Because the property of equality said so, right? It doesn't change the equation's value. It doesn't unbalance the equation because I've added the same value to both sides. So my answer then is what I want to show you as two different ways to get it. Okay, so this is method one. And it's an improper fraction approach. And if I'm being very transparent, this is the only approach that I was ever taught. So what we need to do is we need to have 3 1/3, and we have to have 2 1/2, and we have to add them together. So the first thing we're going to do is we're going to change them both into improper fractions. So 3 times 3 plus 1. 3 times 3 is 9, plus 1 is 10. So this is 10/3. Do the same thing over here. Good grief. 2 times 2 is 4, plus 1 is 5. So I have 5 halves. I need to either get common denominators, or we can apply the definition that we saw before, since they don't have anything in common. So 10 times 2 is 20, plus 3 times 5 is 15, divided by 2 times 3, which is 6. Multiply each diagonal, multiply the denominators. Adding the numerator, I have 35. So my answer is 35 out of 6. I actually am not allowed to leave this as 35 out of 6. So if a problem starts out with mixed numbers, the answer needs to be in mixed numbers. If the problem starts out with improper fractions, the answer needs to be in improper fractions. So I do need to take the 35 and divide it by 6. It will go in 5 times, leaving me with a remainder of 5. So this is 5 and 5 6. There's lots of steps to that. Lots of converting in and out of the mixed value notation, mixed number notation. Any questions on any of those steps? So this is one option. Sometimes when we learn one way, we always want to do it that way forevermore. I actually don't think this is a very good option to use, and I'll show you the other option and maybe you'll like it too. If not, that's okay. So method 2 is to do it with mixed numbers. So we have 3 1/3 and 2 1/2. So what we do is we pull the whole number pieces together and we put the fraction pieces together. So 3 plus 2 is 5. And then I do still have to get common denominators. I mean, I still have to combine those pieces together. So I'll still use that same algorithm that I did before. So I have 1 times 2 is 2, plus 1 times 3 is 3, over 3 times 2, which is 6. And I end up getting 5 and 5 6. This is a very simplified example. It was really nice that the answer at the end was 5 over 6 and not say like 10 over 6, right? If the answer at the end had been improper, I would have had to do a step to actually convert it. But one of the reasons that I like this so much is that it keeps the value smaller. And at least part of the time, it avoids me having to convert anything back into mixed numbers anyway, because it stayed mixed along the way. So this is a separate approach that you can use. Sometimes it asks you to do something specific. On a test, I might ask you to do it in 2 different ways. I've done that before on this test, this one that you have coming up. Let's do it 2 different ways. Otherwise, you're welcome to do it in whatever way you like. Okay, so if it doesn't indicate, you get to pick. So let's move on into subtraction. So by definition, subtraction, a over b minus c over d, yields a value e over f, such that a over b equals c over d plus e over f. And that looks really messy. So let me just show it to you with some whole numbers because I think it's easier to see why it works. The reason that 5 minus 2 is 3 is because 5 is equal to 3 plus 2. And that's all that definition is saying, is that this value over here that it's equal to is what happens when you add that value to the other side. That's showing up that way. And then theorem 6.8 talks about what happens when you think about addition as adding the opposite. So a over b minus c over d is the same thing as a over b plus negative c over d. It's the addition of a negative. All right, so now we're going to actually look at what happens when you have like versus not like denominators. Okay, please remember, if you haven't yet, you can print all these notes out online so you're only filling in blanks instead of writing a whole bunch of stuff down too. All right, so subtraction of rational numbers. If a over b and c over d are rational numbers, so they have the same denominator, b, then just like with addition, we just subtract across the top. A minus c over b. If the denominators are different, we do like we did before, where we multiply the first diagonal, then we will subtract as opposed to add the second diagonal, and we'll multiply along the bottom. So we have the same smiley face showing up. So we're going to do an example now that has some subtraction involved in it, but it also has some mixed numbers as well. So it's a combination of some of the things we've talked about today. Martine bought 8 3/4 yards of fabric. She wants to make a skirt using 1 7/8, pants using 2 3/8, and a vest using 1 2/3. How much fabric will be left over? So the first thing to recognize is what it is we're actually being asked to do with all these values. So we're starting off with this big old long sheet of fabric. It's 8 3/4 long. And if you imagine what she's really going to do as a seamstress, she's going to lay it out and she's going to literally cut off one piece, and that's going to be the first piece. And then she's going to cut off the second piece, and that's going to be the second piece, and she's going to cut off the third piece. So as she's cutting each of these pieces off, she's removing them. That's subtracting them off of the larger piece she started with. So she's going to take off the 1 7/8, and then she's going to take off the 2 3/8, and then she's going to take off the 1 2/3. Does that make sense? Another way to think about this is you could add up all the things that she's trying to make and add those together first, and then subtract that big value of what those are added up to from the original one. And that is perfectly fine if you think about it and do it that way. Neither one's easier than the other. They're just slightly different. Okay? And what you notice, or should notice, is that we have mixed numbers here, right? And so again, that means that we have 2 approaches that we can do. So I'm going to show you what happens on this one in particular with the 2 different approaches so that you can see kind of a little bit of a hiccup that comes into the mixed number approach that was so beautiful last time and worked so simply. So let me actually first do that improper fraction approach. So method 1. We're going to do it as improper. So improper is going to give me some larger numerators, right? I'm going to have to do multiply around on each of them and add on every single one. I'm going to have to do it 4 times. So I have 4 times 8 is 32, plus 3 is 35/4, minus 1 and 7/8. So 8 times 1 is 8, plus 7 is 15/8. 8 times 2 is 16, 17 is 19/8. We have negative 1 and 2/3, so 3 times 1 is 3, plus 2 is 5/3. Now, if you want to, you can combine the two in the middle because they're both 8ths. That's fine. I'm just going to leave them for now and do it all in one step of combining. But I need common denominators, and while it's been lovely when we've got two values and I can do my little cross thing with the smiley face and all that's really great, I have 4 of them here and 3 of them that are distinctly different. So I'm going to do this just a little bit differently. I'd like to get a common denominator for 4, 8, and 3. And while I could just multiply 4 times 8 times 3, that's a little bit overkill. And the reason it is because if I multiply 4 times 2, I already have 8. Does that make sense to everyone? So I can multiply by 2 here so that I get the 8 in that denominator, and by the 8 here so I get an 8 in this denominator, and then the other two already had an 8. And then I've got a 3 in the last denominator, so I need a 3 in the other denominators as well. So I'll multiply numerators and denominators of each of them by 3. The numbers got big all of a sudden, didn't they? They actually kind of did. So we have 3 times 2 times 35. My first denominator is 210. I'm sorry, numerator is 210. And my denominator on all of them should be the same as 24. The second numerator is 15 times 3, which is 45 over 24. Then I have 19 times 3, which is 57 over 24. And I have 5 times 8, which is 40 over 24. Once the denominators are all the same, I can subtract the numerator. So 210 minus 45 minus 57 minus 40 all over 24. So it's 68 over 24. There's 2 problems with 68 over 24 as a final answer. What's something you see that's a problem with it? It's not reduced, and by that, I hope what you're saying is that they're both even on top and bottom. That's right. What else is the problem? Once we get it reduced, there's still going to be a problem. It's not a mixed number. So you can do that in either order, but I think that the division we have to do will be easier if the numbers are smaller, so I would reduce first. They're both at least divisible by 2. So if you weren't sure what to do next, we could at least start there. So 68 would become 34, and 24 would become 12. And then we see that they're divisible by 2 again. So 17 and 6. It's a lot easier to divide 17 by 6 to get my mixed number. So we have 17 divided by 6. It goes in 2 times. Remainder of 5. This is 2 and 5, 6. What? Yards. 2 and 5, 6 yards. Okay. Those numbers were not the nicest numbers to work with for multiple reasons, but one being that there was 4 of them and one being that they're large, and maybe there was something else too that you didn't care for much about them. I would like to do the problem one other way, and that's with my mixed number approach. It's not as friendly as it was before, but I still think that it has merit for being a contender and being just as easy anyway. Okay, so I'm going to copy this over. This is my starting point. You can ignore all my red arrows. Let's see if I can delete them all, because I'm not changing them into mixed numbers. I can at least delete the red circle part of them without getting too involved. But when I have a mixed number that says, for instance, like this negative or the subtraction of 1 and 7/8, it's subtracting 1 and it's subtracting 7/8. So very literally, I have 8 and I have 3/4, and those are both positive, and then I have a 1 and I have a 7/8, and those are negative, etc. Are you guys with me on that? So I'm subtracting whole number pieces and I'm subtracting fractional pieces along the way. So as I separate these and put the whole numbers at the beginning for the subtraction and I put the fractions at the end, I need to be very careful not to lose the sign that's attached, because that is a common mistake. So I have 8 minus 1 minus 2 minus 1, and then I have 3/4 minus 7/8 minus 3/8 minus 2/3. Whole number pieces are great. 8 minus 1 minus 2 minus 1. What do I get? Yeah, I have 4. Then I need common denominators, much like I did on the previous slide. It's just that I don't have as big a numerators that I'm going to have to deal with. So on the first one, I know my number is going to be 24, so I'm going to cut to the chase a little bit by writing this down as like times 6, times 3, times 3, and times 8. So I end up having my number 4, and then I have 18, minus 21, minus 9, minus 16, all over 24. To subtract that numerator, 18 minus 21 minus 9 minus 16, what do you get? First of all, it's negative. So there's a subtraction sign here. It's 4 minus what comes next. What's that numerator? Anybody do it? 28 is what I have written down. Does that sound okay? Cool, we'll go with 28. Much like the problem before, they're even on top and bottom, right? And in fact, I might even recognize this one more readily as both being divisible by 4 when I maybe didn't necessarily before. So this is 4 minus 7/6. I cannot just leave this as 4 minus 7/6. Okay? So there's a couple of things you could do. One option is that you could recognize what 7/6 is. That is, turn the 7/6 into a mixed number. And I don't think that's a bad approach. So 7/6 is the same as 1 and 1/6. Agreed? So I can take my 4 minus 1 and 1/6, and I have another whole number piece to take away from the 4. 4 minus 1 is 3. But the 1/6 is still subtracted. And this is what I have. I have 3, and I have a negative 1/6. So can you imagine, let's actually do this without the number 1/6, then imagine it's quarters. Imagine you had $3 and you were supposed to subtract away a quarter. Well, if you have 3 $1 bills, you can't just like turn a dollar bill into coins. I mean, it doesn't work that way. But you kind of can. You can take a dollar bill and you can turn that dollar bill into 4 quarters, right? So what we can do is we can take one of these units that are in the 3s and we can turn it into the quarters. There's 6/6. And now that I have the $2 or the 2 whatever in front, in this case yards, and I've got the 6/6 of it, just like my 4 quarters, now I'm able to remove one of those 6. So now I have 2, and 6 minus 1 would be a 5, 6 yards left over. Okay? This requires a little bit more thought process. It's not quite as rigid like, here's step number 1, here's step number 2, here's step number 3, as it is with improper fractions, but it does work. Okay? So it's another option. All right, have one more thing in this section of material. We're going to take a look at convenient fractions. When we are trying to estimate, some fractions are just not friendly to work with. And especially if we're estimating, we often don't care about the exact value anyway. So these are fractions that are roughly equal to what we're given, but they're easier to work with, like 0, 1/2, 1/3, all the way to 1. So most of these are fractions you've used in some fashion before for different things. So what we're going to do is we're going to take a couple of sort of unfriendly fractions and change them so that they're approximately equal to what we started with, but friendlier, more convenient to use to work with. 12/78. I mean, I know they're both even on top and bottom, so we could like legit reduce. I get that. But 12 and 78 themselves are not very convenient. But it's actually true that 12 is pretty close to 10 and 78 is pretty close to 80. Right? And I bet 10/80 in your mind looks an awful lot like 1/8. Doesn't it? 1/8 is a pretty reasonable fraction. If you go buy medium pizzas, they're cut into 8 slices. Imagine one slice of pizza. And you have the picture in your mind of 1/8. Okay? It asks in the directions, though, to decide if your estimate is high or low. So I will tell you that it's not going to ask you ever to justify that. So if you really like decimals and you want to turn them both into decimals and just see which one's bigger, you can do that. There's ways to reason through what's happening as well. For example, if I take the numerator 12 and I make it smaller, right? Moving from here to here made it smaller. And to be honest, when I make the denominator bigger, I cut it into more pieces. So I make it also smaller. So both operations that I did made the value smaller. And since I've made both the top smaller to change the fraction, I've made the bottom smaller, which changes the fraction. This estimate is a low estimate. It's smaller than what I started with. So whatever answer I'm getting, I just recognize it's going to be a little bit smaller than what the real answer should be if I'm using this in an operation of a problem. 2/1001. So I'm going to show you 2 different ways to do this because it depends on the directions and how they're given. If they're given like I've written it here, then it's pretty convenient to say, hey, 2's fine, but I mean 1001's awfully close to 1000. Agreed? And then I can divide them both by 2, and I have the fraction 1/500. Now, if I've only changed the denominator, in this case, I made the denominator smaller, which means that I make the overall fraction, I'm just going to write it here, it makes the whole fraction bigger. Okay, the denominator didn't become bigger, but the fraction became bigger. Because instead of dividing it among 1001 people, I'm only dividing something among 1,000 people. Right, so everybody gets like 1 bite more of the fish and loaves or something, whatever, I'll know. Okay, so it's slightly bigger. So this is a high estimate because I made the fraction slightly bigger. If your directions instead, and you will have a direction set instead that will say choose a convenient fraction, and it's almost like multiple choice. 0, 1/4, 1/2, 3/4, or 1. It gives you choices. It's like multiple choice. Which of these fractions, which of these numbers, is the closest to 2/1001? 0. The number 2/1001, which is approximately 1/500, is very, very small. It's practically speaking 0. So you would say, if that were your direction set, that your answer is 0. And of course, 0 is smaller than what you had, so it would be a low estimate if that were what you were given to work with. Does that make sense? Okay. All right, so I'm going to make you a deal. We're going to go ahead and assign this without group work done today because we don't have time for the group work, but I will definitely make sure that we do group work for 6.3. Okay, even if it bleeds into an extra day, a little portion of a day or something. But I don't really want us to pause on this one just yet and get already a half of class period or therefore thereabouts a day behind. So we're going to go ahead and say that this one's due on Friday. The group work, you're just going to do it first on the sheet of paper, homework after it, turn it all in. Obviously, you're welcome to work outside of class with one another, with the tutors in the Success Center, or to come see me if you need help. Okay, we will start just like we did today with about 10 minutes or so of questions next time. If you have a couple, that's probably fine. If you have more than a couple questions, you probably should be seeking help from one another or someone else that can help you outside of class.